Okay, well, now we're finally ready to get down to what our goal was all along and to review how can you determine whether a molecule is aromatic or not. So here's the basic rules. And actually, as you may already know, there's actually three different categories. Some molecules are aromatic, some molecules are called anti-aromatic, and some molecules are called non-aromatic. Aromatic, anti-aromatic, and non-aromatic. Let's review what the basic meaning of all of these terms are. So aromatic, one of the most interesting properties of aromatic molecules is that they are more stable than you might expect. Aromatic molecules are especially stable. So aromatic means very stable. Or at least aromatic molecules are a type of molecule that's very stable. Now, how about anti-aromatic? Anti-aromatic molecules are particularly unstable. They're less stable than we might have expected. So anti-aromatic indicates very unstable. And non-aromatic just means normal. Neither particularly stable nor unstable. So a non-aromatic molecule is just a normal molecule, like you would have studied all through the first semester of OChem. So all through the first semester of OChem, you didn't use these terms aromatic and anti-aromatic because you were just studying normal, non-aromatic compounds. So this means very stable, this means very unstable, and this means normal, not especially stable or unstable compared to what we would otherwise expect. So I've put on the board the basic rules for determining what category we're going to fall into. One thing to notice here is that in order to be either aromatic or anti-aromatic, you've got to be cyclic. That is, you have to form a ring. Anything that is not cyclic is just a normal non-aromatic compound. Also, you have to be flat to be in either of these two categories. If you're not flat, you're non-aromatic. And actually, we're not going to worry too much about this idea of being flat because in many cases, you can't really tell whether a molecule would end up being flat or not without actually building a model, which is not something you'd normally be expected to do on a practice problem maybe or a test question. So actually, I think that most of the examples we're going to do, we're just going to assume that they're flat. Usually that's what the instructor would expect you to do on test questions as well. We're just going to assume that molecules are flat because you really can't figure it out just by looking at a molecule in most cases, or at least I can't. Okay, so what category does butane fall into? Well, butane is not cyclic. Since it's not cyclic, it's just a regular non-aromatic compound. So butane is non-aromatic. We also have this concept of completely conjugated. Now, most of you have probably heard a definition of the word conjugated. The definition you've heard is probably that conjugated means alternating single and double bonds. Most people are told that the word conjugated means alternating single and double bonds. But actually, that definition is not general enough to use at this point in an OChem class. So we're going to have to kind of give up on that definition. Even though that definition is right in a sense, it's too specific. We need to generalize it. Anything that has alternating single and double bonds is conjugated, but there's other types of molecules that are also conjugated even though they don't have alternating single and double bonds. So what's the better definition of completely conjugated? Well, the best definition of completely conjugated is that completely conjugated means side-to-side overlap of p orbitals at every atom in the ring. I'll say that definition again. Completely conjugated means side-to-side overlap of p orbitals at every atom in the ring. So here's our new and improved definition of the term completely conjugated. Completely conjugated means side-to-side overlap of p orbitals at every atom in the ring. Go ahead and copy this down carefully into your notes. because in a second I'm going to erase this so I can have some room to show some examples. First of all, let me just remind you what side-to-side overlap of p orbitals means. So hopefully you know that the shape of a p orbital is like this, kind of a figure 8 shape. P orbitals look like this. So what would it look like if we had side-to-side overlap of p orbitals? Well, that would happen if you have two orbitals arranged like this. And notice that we have an overlap of this side of this orbital with this side of this orbital over here. We can use dotted lines to indicate the bonding interactions between the lobes of the p orbitals. This would be side-to-side overlap of p orbitals. What I've shown so far is a side-to-side overlap of p orbitals at two atoms. Here's a p orbital at one atom, and here's a p orbital at another atom, so I've shown side-to-side overlap of p orbitals at two atoms. What's the alternative to side-to-side overlap? The alternative to a side-to-side overlap is head-to-head. So here I've drawn two p orbitals that have head-to-head overlap. So here's one p orbital at this atom, here's another p orbital at this atom, and you can see here the bonding overlap between these two p orbitals, and hopefully you can see why this would be called head-to-head overlap, because the head of one p orbital is overlapping with the head of the other p orbital, and hopefully you can see why this is called side-to-side overlap. The heads are not overlapping, but instead this whole side is overlapping with this whole side over here. One important thing to notice is that side-to-side overlap of p orbitals requires the two p orbitals to be parallel to each other. The reason that this p orbital is overlapping with this one is that they're both pointing in the same direction. They're both parallel to each other. That is, they're both vertical. If this p orbital had been horizontal and this one was vertical, then they couldn't have a side-to-side overlap. Okay, so that's what the term side-to-side overlap means in our definition of completely conjugated. But for the most part, I'm not going to talk about that too much more. The main thing I'm going to focus on is that in order to be completely conjugated, if you look at the definition, you can see you can only be completely conjugated if you have a p orbital at every atom in the ring. You can't be completely conjugated unless you have a p orbital at every atom in the ring, because if there's no p orbital, how can there be side-to-side overlap of p orbitals at every atom in the ring? Is this molecule completely conjugated? Well, what's the hybridization of each of the carbons? Using the work that we did previously, using the basic rule for hybridization, you should be able to see that every atom in the ring is sp2. All of these atoms are sp2. So do they have any p orbitals? Well, yes. Using what we talked about a few minutes ago, we know that any sp2 hybridized atom has one p orbital left over. So there's a p orbital here, 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 and a p orbital here. So is this completely conjugated? Yes. Because there is a p orbital at every atom in the ring, we can have that side-to-side overlap of p orbitals at every atom in the ring. Of course, you would already have known this was completely conjugated even if you just used the definition of alternating single and double bonds. But now we can see our new definition works as well, overlapping p orbitals at every atom in the ring. Is this molecule completely conjugated? Well, first we have to find the hybridizations. And again, every atom in this ring is sp2 hybridized. sp2, 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 and this atom is also sp2 hybridized. So do they all have p orbitals? Yes, since they're all sp2, they all have p orbitals. So we can have overlapping p orbitals at every atom in the ring. So yes, this is also completely conjugated. This molecule is completely conjugated. And now notice that the old bad definition of completely conjugated wouldn't have worked here. Again, maybe before you watched this video, you might have learned that completely conjugated means alternating single and double bonds. But this molecule does not have alternating single and double bonds. They're alternating down here, double, single, double, but then we have two single bonds in a row, single, single. So using that old definition, you would think this is not completely conjugated, so it's time to throw that definition away. That definition actually doesn't work. We need to use our new definition of completely conjugated. Completely conjugated means side-to-side overlap of p orbitals at every atom in the ring. Since these are all sp2, they all have p orbitals, and we can have that side-to-side overlap of p orbitals at every atom in the ring. So yes, this is completely conjugated.